Question number 6.228. A P32 radionuclide with half-life T equals to 14.3 days is produced in a reactor at a constant rate, which is given Q equals to 2.7 into 10 to power 9 nuclei per second. How soon after the beginning of the production the radionuclide will its activity equals to A 1 into 10 to power 9 disintegration per second. Okay, so in this case the production rate is given, which is 2.7 into 10 to power 9 nuclei per second. Half-life of this nuclide P32 is given, that is 14.3 days, and we have to find out the time when activity becomes 1 into 10 to power 9 disintegration per second, right? So first of all, we have to find out production of nucleus, okay, in this case, with which rate nucleus production is taking place, right? So this rate of production can be written as dN over dt, okay, and it must be equals to the rate which supply is taking place. So we can say supply minus the rate of dt per second, right? So the supply rate is Q and decay rate is lambda into n, where lambda is rate of decay, okay. So we can write expression of nuclear production is dN over dt, which is equals to Q minus lambda into n. So here we can use our mathematical skill just by we can just multiply by e to power lambda t in this entire equation, and let's see what we'll get. This is e to power lambda t into dN over dt is equals to e to power lambda t into Q minus lambda into e to power lambda t into n, right? So we can write this entire expression in form of differentiation. It will shift this term on left side. So we can rewrite it as e to power lambda t into dN over dt plus lambda into e to power lambda t into n, that is equals to e to power lambda t into Q, okay. So this term can be combined as d over dt into n e to power lambda t, right? If you expand this term, then we'll get same expression, okay. So basically we are using mathematics in reverse order, right? So from here we may write that n into e to power lambda t is equals to integration of this segment, right? So by solving is, or we can say integrate both sides, what we are going to get that n into e to power lambda t, which is equals to Q over lambda into e to power lambda t plus certain constant. Because here limit are not known, we are performing indefinite integral, then we need to introduce a constant term. Now we can find out this constant term by applying initial conditions, that at time t equals to 0, there is no nuclear, so n is equals to 0. Now if we substitute in this expression, then what we may get that Q over lambda plus constant is equals to 0. It means constant is equals to minus Q over lambda. So we can rewrite this expression. This is the solution what we have got from this differential equation, that is n into e to power lambda t, which is equals to Q over lambda into e to power lambda t minus Q over lambda, right? Now we can eliminate this term e to power lambda t from this entire expression to get a proper expression for n, that is n is equals to Q over lambda we can take out this term, that is 1 minus e to power minus lambda t. Okay, this is our final expression. Okay. Now, we can calculate activity of this sample. That activity is equals to lambda into n. Okay, so if you substitute n from there, then we'll get A is equals to Q into 1 minus e to power lambda t. This is our final relation. Okay. That how the supply rate of the nucleus and final activity rate what we wanted. Okay. So we can substitute these numeric values in this expression, right? So we may write here that 1 into 10 to power 9, which is amount of A, is equals to Q, which is 2.7 into 10 to power 9 into 1 minus e to power minus lambda t, right? So from here we'll get 1 over 2.7 is equals to 1 minus e to power minus lambda t, and we can write e to power minus lambda t is equals to 1 minus 1 upon 2 to power 7. Okay. So by taking natural log on both sides, we can calculate lambda t, right? So lambda t is equals to ln 1 minus 1 upon 2.7. Okay, or we can say 1.7 upon 2. Okay, let me write here 1.7 upon 2.7. So from there we'll get lambda t is equals to 0.463. Okay. Now we have to calculate time. So time is equals to 0.463 over lambda. Here lambda is not known, but half-life is given. Okay, and we already know that half-life is equals to ln 2 upon lambda. So from here we can replace lambda by ln 2 upon half-life. So this expression can be rewritten as 0.463 into half-life upon ln 2, right? And half-life is given, that is 14.3 days, right? So we can rewrite here. Okay, let me write here that given time t is equals to 0.463 into 14.3 days divided by 0.693, it is value of ln 2, right? So from here we'll get 9.5 days. It means after 9.5 days, the activity number of this nucleides will be 1 into 10 to power 9 days per second.